In Section 8.4, we introduced a different type of graphing and equation called the parametric equation. If f and g are functions defined on an interval I, then the set of points, f of t, g of t, is a plane curve. The equations x equals f of t and y equals g of t, where t is in the set of I, are parametric equations for the curve with parameter t. This is going to be kind of like traditional graphing, except for the input being t is going to mean when we graph, we're going to have to pay attention to the direction of the graph because the graph is being done over a period of time. Let's look at sketching the curve of parametric equations. So let's start with the equations x equals t squared minus 3t and y equals t minus 1. Now what happens is we're going to do this with a table. Now you're probably going to do it in the calculator like I showed you in class, but I'm going to set up a table here because the way this is going to work is for values of t, you're going to plug them into both x and y. And the ordered pairs that are going to get graphed are going to be the x, y ordered pairs. So if I plug negative 2 in to x, I get 10 as my output. And when I plug negative 2 into y, I get negative 3 as my output. So we're going to plot the point 10, negative 3. If I plug in negative 1, I get 4 as my output for x and negative 2 for my output for y. If I plug in 0, I get 0 for x, negative 1 for y. If I plug in 1 to x, I get negative 2 for x, and I get 0 for y. When I plug in 2, I get negative 2 for x and 1 for y. When I plug in 3, I get 0 for x, 2 for y. When I plug 4 in for t, I get 4 for x and 3 for y. And when I plug in 5, I get 10 for x and 4 for y. So these are the ordered pairs that I'm going to graph. So now when I look at this graph, let's see, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, So I'm going to graph negative 10, 3. I'm going to graph 4, negative 2, which is going to be about here. 0, negative 1 is here. Let's see, I need some more tick marks over here. Negative 2, 0. Negative 2, 1. 0, 2. 4, 3. And 10, 4. And we end up with this sideways parabola. Wait a second, we've talked about sideways parabolas. Now what I want you to do is I want you to graph this in your graphing calculator and look at the direction of travel. What you'll notice is that when the graphing calculator graphs it, the motion moves in this direction. So what would happen then if I replaced t with negative t in those equations? Well, x would become t squared plus 3t, because if you put in negative t squared is still positive t squared. And then when you plug in negative t in the second part of the equation, you get negative 3 times negative 1, which is negative 3. Y becomes negative t minus 1. When you graph these in the graphing calculator and you go and look at the graph, what you're going to notice is that the direction of travel changes. It instead goes this way. Well, then what's going to happen if I replace t with 2t? Well, first of all, the equations change. So x is 4t squared minus 6t. Y becomes 2t minus 1. When you graph it, again, the graph looks the same. However, because it's graphing, what's happening is it's going to graph over a faster period of time. It only has a certain amount of time under which it graphs, so sometimes you don't see the entirety of the graph, you don't see the entirety of the parabola. When you replace t with 2t, it graphs twice as fast, so sometimes you'll see more of the graph. What happens is we have a parametrization that contains more information than just the shape of the curve. It also indicates how the curve is being traced out. So sometimes it goes one direction, sometimes it goes the other direction, and sometimes it goes faster than normal. So we had just determined that this graph we got was something we'd seen before. When we did conics, we talked about parabolas that open left or right. So one of the things we can do is we can eliminate the parameter and see what the equation would be in rectangular coordinates. So let's use those same two equations and eliminate the parameter. Now the easiest way to do this is to take this second equation and solve it for t. So t is going to equal y plus 1. Then we're going to substitute that into the x equation in place of t. So x is equal to y plus 1 squared minus 3 times y plus 1. So that's y squared plus 2y plus 1 minus 3y. Let's see, I don't need, darn it. This doesn't have an eraser, so instead of erasing, I kind of have to just go back. Let's see, y squared plus 2y plus 1 minus 3y minus 3. And then when I combine my like terms, I end up with y squared minus y minus 2. And this was a parabola that opened to the left. And we had learned how to put it in vertex form so that we could determine the vertex and how it was graphed. But at least we know this is the rectangular coordinate version of the parametric equation. Now let's talk about circular motion. Now we're going to use some parametric equations using trig functions. So I want to describe the graph and the path of the object using the parametric equations x equals cosine t and y equals sine of t, where t is greater than or equal to 0. Well, if you go and graph this in your calculator, you're going to notice that it's a circle. Well, cosine squared t plus sine squared t equals 1 was one of our Pythagorean identities from when we studied trigonometry. Well, if you notice x is cosine t, that means cosine squared t must be x squared. And since y is sine of t, that means sine squared t must be y squared. So you get x squared plus y squared equals 1. That's the equation of a circle that's centered at the origin whose radius is 1. And when you graph the parametric equation, you notice you get the same graph. When you graphed it, it went in a particular fashion. It went that direction. And the object completes one revolution around the circle in 2 pi seconds. Now let's talk about eliminating a parameter when we're dealing with parametric equations with trig functions. So I'm going to eliminate the parameter and sketch the graph of this parametric equation. First of all, you can graph it on your calculator and you'll see what happens. You end up with this graph that looks something like this. And it probably graphs this direction first and then this direction second. Well, what's really happening is first it goes up like this and then it goes back down. It's just you don't see that because it's sketching over the actual curve. And then it comes over here and goes up this way and then it goes back down this way. So there's part of this you're not seeing on the calculator. Alright, so now let's go and talk about eliminating the parameter. Well, in order to plug one equation into the other, I need to have the same trig function, which I don't. One equation has sine, one equation has cosine, so I need to change one of the equations so it has the same trig function. Well, the only one I can really work with is this one. The reason is because we learned that cosine squared t is the same as 1 minus sine squared t. And now I know that sine is x, so sine squared is x squared. And I'm going to do a little simplifying. So I'm at 2 minus 1 plus x squared. So y is equal to 1 plus x squared is the equation that's being graphed. And that makes sense because the graph, when we put in our calculator, it is a parabola because x squared is a parabola that's been shifted up 1 unit. The other thing that I want to look at with this particular problem is what its domain is. Well, we know that since we changed everything to sine, sine has a particular interval. It fluctuates between 1 and negative 1. And since we said that sine is the same as x, that means that our x values can only fluctuate between 1 and negative 1. The last thing that we're going to talk about in this video is finding a parametric equation for a graph. I want to find a parametric equation for the line that has a slope of 3 and passes through the point 2, 6. Well, I want you to think about what that looks like. So here's my graph. 2, 6 would be 1, 2, 3, 4, 4 would be here. If it has a slope of 3, that means to get to the next point you would have to go up 3 and to the right 1. So your line would be here somewhere. Now, to make the parametric equation, we're going to use the fact that the slope is 3, and we're going to go back to our old definition of slope, which is rise over run. Here's my run, which is going to be 1 unit, and my rise, which is 3. Well, since 1 is a change in x, we're going to say that x is 1t. Now, the reason it's 1t is because, remember, this is parametric, and we're making changes over time. And y is going to be 3t. That's how it's changing over time. Now, we have to use the fact that we know that it passes through 2, 6. So to finish my parametric equations, all I'm going to do is I'm going to add 2 to my x, because 2 is the x-coordinate of the ordered pair, and I'm going to add 6 to the y-coordinate. So there are my parametric equations. If you were to graph those parametric equations, you would get this line. Now, to go back and find out what this equation is in rectangular form, remember we like to solve one of the equations for t. So I'm going to solve this for t, and I'm going to find out that t is equal to x minus 2. And then I'm going to plug it into the other equation. So y is equal to 3 times x minus 2 plus 6. So it's 3x minus 6 plus 6. The 6's cancel, and you find out that it's the equation of y equals 3x. So the graph that I drew on the picture did not do it any justice. It should have looked more like this, so I apologize for my bad graph, but you get the idea of what is happening.